Quantum mechanical problems can often be reduced to linear algebra with operators represented by matrices and functions represented by vectors. Indeed, the general mathematics that we've set up for quantum mechanics is in exactly this form. The practical solution of some problem then, such as finding the energy eigenvalues and eigenstates, can actually be reduced to a problem of finding the eigenvectors of a matrix. In such a matrix form, though, commonly no exact analytic solution is known. Then we may have to solve numerically for eigenvalues and eigenvectors, which means we have to restrict the matrix to being a finite one. Mathematically, that means we're only considering a subset of all the possible basis functions that could be considering for a problem like that. As a result, we could call an approach like this a finite matrix or a finite basis subset approach. Now, the use of finite basis subsets is quite common. Indeed, it's routine in many numerical calculations. But this particular approach is not normally discussed explicitly in quantum mechanics texts, at least not with any specific name. However, it's so useful and so simple with modern numerical techniques that we're going to look at it explicitly here. Actually, in some analytic problems in quantum mechanics, we can also use such finite basis subset approaches. This approach is taken, for example, in what's called the K.P method of calculating band structures in semiconductors. And this is the principal band structure method used for calculating optical properties in, for example, semiconductor lasers. The overall problem is very complicated, but we pretend that only a few of the so-called bands in the material are really important. And we solve essentially exactly and even analytically for that simplified problem. In general then, in a finite basis subset approach, what we're doing is saying that we're going to make an essentially exact solution, but to a simplified version of the problem. Though the problem really needs a possibly infinitely large basis set for its exact solution, we are presuming that we only practically need to make a much smaller subset of those and then solve that problem with standard techniques for finite matrices. In practice, in such an approach, we have to choose the finite basis subset with care, and in the end, there is no substitute for intelligence in making that choice. This is something of an art. If we choose the form of the basis set badly, or we make a poor choice as to what elements to include in our finite subset, then we'll end up with a poor approximation to the result, or possibly even a matrix that is ill-conditioned. A very frequent choice of a starting basis set is to use some of the energy eigenfunctions of the unperturbed problem, or at least those of a simpler, though related problem. So let's try to use such an approach here for our problem of an electron in a box with an applied electric field. So, to set up our finite matrix method, which is the same thing as our finite basis subset method, as we could call it, for an electron in a well with field, we'll need to construct the matrix of the Hamiltonian for the problem. Well, that's straightforward. The matrix elements are simply these bra operator ket products here. And for a simple one-dimensional function here, this just reduces to some integrals. So we've split the integral into two parts, one with the differential operator corresponding to the kinetic energy, and another with the potential energy here, F times Xc minus a half. In this particular case, because the wave functions are real, the complex conjugation makes no difference. In the integral for this matrix element, which we can call Hij, if we choose the energy eigenfunctions of the unperturbed problem to form our basis set, which we've sort of implied here with this notation anyway, then these eigenfunctions, we know what they are, and we can easily perform this whole operation analytically. The derivative is fairly straightforward. Second derivative of sine is going to give us minus sine with some coefficients out front. And the resulting integrations can also be solved analytically in this case, or you could simply perform them numerically. For our explicit example that we have here, we're going to consider a field of three dimensionless units. That is, we're going to choose f equal to 3.
with the first three energy eigenfunctions of the unperturbed problem as our finite basis set. That is, although in the ideal problem we would use an infinitely large basis set, we're only going to use the first three elements of this particular set and see how we get on with that. Then we can evaluate the matrix elements, these quantities h, I, j, and that gives us our Hamiltonian matrix. So simply calculating through with these examples here, here's our matrix. It's got the unperturbed energies down the diagonal, you will see, and then various quantities on the off diagonal. Now, not surprisingly, if you look at the mathematics, these numbers are actually equal here. And of course, this operator, this matrix, is Hermitian. As we would expect, it's just a Hamiltonian. So this element here and this element here are complex conjugates of one another. Well, they're real numbers, so that's rather trivial, but it's still true that this element is the complex conjugate of that one, and this element is the complex conjugate of that one. Now, numerically, we can find the eigenvalues of this matrix. There are various computer techniques we could use, or this one is simple enough, we could just do it by hand. And the answer to that is that there are three eigenvalues of this matrix. Eta 1, 0.904, so that means the first energy level is 0.904 of our energy units. The second energy level, eta 2, is 4.028 of our units. And the third energy level, the third eigenvalue, is 9.068 of our units. And you'll notice, first of all, these are quite close to the unperturbed values, the ones we would get at zero field, which of course would be 1, 4, and 9, respectively, for an infinitely deep well in these units. We see also that our lowest energy eigenvalue here has reduced from its unperturbed value, so it's 0.904 now instead of being 1. Incidentally, we can solve this problem exactly. The results require the use of Airy functions, and so we can write down the exact answers to this problem. The first energy level would be 0.90419, so obviously that's essentially the same. The second one would be 4.0275, so that's obviously actually the same. The third one's a bit off. We shouldn't actually be surprised at that, and that's in part because we only put 3 of these basis functions into our problem. However, we can see for the first level, this is looking really very good. The corresponding eigenvectors we can solve numerically as well, and we get the first one here, the second one, and the third one. This is the one associated with the first energy eigenvalue, this with the second, and this with the third. Incidentally, these eigenvectors here have been set up to be normalized. The sum of the squares of these 3 elements, for example, adds up to 1, and the same is true for these 3, and the same is true for these 3. So explicitly then, writing out what the first eigenfunction really is, it's this function. So it's 0.985 times that first unperturbed eigenstate plus 0.174 times that second state in our basis set plus 0.013 times that third state. So the 0.985 is here, the 0.174 is here, and the 0.013 is here. We can plot out the wave function. Here's a comparison of the unperturbed wave function, so that's just our sign in the well here, this green one, before we put the field on, with the perturbed one that we get as a result of doing this particular calculation using our finite basis or finite matrix method. That's the red one here. We see that the electron wave function has moved to the left with field, which makes sense to us because, remember, we had a slope on the potential like this, so we might expect the electron to run down to the left. Adding more elements to this finite basis here really makes negligible change to this first calculated solution. We can look at the probability density that we get from that wave function, and we find the same kind of thing, of course. The first one, without perturbation, the green one here, is just sine squared inside this particular well, and the perturbed one is just the square of what we were looking at before. So also the probability density has moved to the left, as we would expect.
So we see with this relatively simple matrix method, we've been able to calculate a relatively realistic solution to our problem. We merely construct the matrix for some given field, matrix element by matrix element, using a finite but reasonably well chosen basis subset. Here we chose the first 3 unperturbed energy eigenstates, and then ask the computer to find the eigenvalues and eigenfunctions of the matrix. Those give us our approximations to the new energy eigenstates of this problem. Now, though this method may not be giving us as much insight into the problem, it's certainly a straightforward and quite general approach as a numerical method.